Hi, this is Dr. Sridevi here. I welcome you to the last topic of our second module, that is green oxidation reaction. This experiment can be designed for postgraduate level students. Here we go to learn how to synthesize adipic acid. It is a green oxidation reaction. Let us see the conventional procedure how we synthesize adipic acid. Industrial preparation of adipic acid uses nitric acid, which is a strong oxidizing acid or a strong oxidizing agent that presents many chemical safety hazards and also environmental risks. Nitric acid can react violently with other organic compounds, causing serious accidents in the lab. Additionally, the use of nitric acid in the preparation of adipic acid results in the emission of nitrous oxide. It is suspected that nitrous oxide is a greenhouse gas which may cause global warming. The non-green component of this experiment is the use of corrosive concentrated nitric acid. This causes the evolution of oxides of nitrogen. The reaction has to be carried out in a fume cupboard, and the oxides of nitrogen need to be absorbed in the water. Here comes the procedure which we follow in a greener technique. We take the use of cyclohexene in the presence of sodium tungstate, potassium hydrogen phthalate and hydrogen peroxide to get adipic acid. So the chemicals required for our experiment are cyclohexene, sodium tungstate, potassium hydrogen sulfate, aliquat, hydrogen peroxide. Now let us see the detailed procedure of synthesis of adipic acid using greener technique. Take sodium tungstate followed by the addition of aliquat and also hydrogen peroxide and potassium hydrogen sulfate. The mixture was shaken and then cyclohexane was added. The reaction mixture heated on a sand bath to reflux for about 2 hours. The progress of the reaction was monitored by observing whether the layers are separated. As the liquid cyclohexane was converted into water-soluble adipic acid, the organic layer will eventually disappear. After 2 hours of reflux, the round bottom flask was removed from the sand bath. Upon cooling, the crude adipic acid was precipitated. The crude sample was recrystallized from water to get pure adipic acid. Once we get the adipic acid, check for its melting point and also percentage yield. Let's see what is the green context of the experiment. First thing is that it eliminates the use of nitric acid, concentrate on atom economy, that is nothing but waste byproducts are minimized and we get a better yield. Use of hydrogen peroxide as an oxidizing agent in place of potassium permanganate or nitric acid, and also we observe the phase transfer catalysis. Here comes the mechanism how the cyclohexene is getting converted into adipic acid in the presence of various reagents like sodium tungstate, potassium hydrogen sulfate, aliquat and hydrogen peroxide. Let me explain you the mechanism in detail. In this experiment, an alternative oxidation procedure will be utilized using sodium tungstate as a catalyst for the oxidation of cyclohexene to adipic acid by hydrogen peroxide. This oxidation process or procedure avoids the need of strongly basic medium as used in the potassium permanganate oxidation procedure, and also generates only water as a byproduct instead of MnO2. Presumably, tungstate acts as an active oxidizing agent, being structurally similar to permanganate. Significantly though, the tungstate functions catalytically with an intermediate tungstate products being reoxidized back to the tungstate oxidation state by hydrogen peroxide. Additionally, this process will utilize a phase transfer catalyst, PTC. PTCs are enhancing the rate of reaction between the chemical species in different phases, that is in aqueous phase and also the organic phase. A small amount of catalyst extracts one reagent, typically an anion, from the aqueous phase across the interface into the other phase so that the reaction can then proceed. In order to do so, the PTC must possess qualities that makes it both hydrophilic as well as hydrophobic. Sodium tungstate is soluble in water, but the cyclohexene is not. When cyclohexene and an aqueous solution of sodium tungstate with hydrogen peroxide are mixed, the two layers will result and no reaction can occur. Being a green chemistry experiment, the use of different solvent besides water is less appealing. In order to allow the reaction to occur in the presence of two phases, a phase transfer catalyst will be added to the solution. PTC are soluble in both aqueous solutions and also organic solvents. Ammonium salts bearing hydrophobic alkyl groups, while still ionic, are frequently soluble in less polar organic solvents or organic systems. Through ion pairing, these salts can bring negatively charged species into the less polar system, allowing the reaction to occur. Since ammonium salt can repeat this process again and again, it is generally used in catalytic amounts, hence the name phase transfer catalyst. So, in this experiment, a commercial phase transfer catalyst formed from potassium hydrogen sulfate and aliquot 336 will be used. The ion exchange will allow the PTC to take the oxidizing tungstate oxidizer from the aqueous layer into the organic layer. This oxidizer is then able to oxidize cyclohexene to adipic acid, during which time the tungstate is reduced to a lower oxidation state. The PTC releases the reduced tungsten intermediate back into the aqueous layer. Since both aliquot 336 and also sodium tungstate function catalytically, only the hydrogen peroxide is needed as a stoichiometric reagent, and we will be using it in large excess. In addition, it is possible to reuse the aqueous layer containing the tungstate catalyst, further increasing the green nature of this experiment. So here we come to the end of green synthesis of adipic acid from cyclohexene. Thank you for your patient listening. So now you can proceed for the second assignment. To complete the course on Green Chemistry, Green Earth, Part 1. Meet you in Green Chemistry, Green Earth, Part 2 very soon. Thank you.